Saxon Algebra 1, lesson 72. Here we are, screeching in to the end of week 19. And we have a two-part lesson. The first part I really like because it's a nice continuation on from what we were talking about last time in lesson 71. The second part of this lesson annoys me, but I'll save that complaint for later. Okay, we've been talking about trinomials. We've been talking about factoring things out of trinomials to make them look cute so that we can factor them. And this time we're going to talk about factors that are sums. What? Well, once I show you, you'll be like, oh, that's obvious. 72.1. They're kind of long, and thank goodness you don't have to write them out yourself when you're doing the homework. As you look at them, you might think, what? That is one nice thing about writing them down, is you can see very clearly that what we have here is a fairly standard trinomial, right? I can see it, x squared, plain x, plain number, but look what's in the way. This big quantity, this sum of a plus b has attached itself like a leech to each part of our trinomial, and I don't want it there. Our same rule holds. Look at the first term. Put them in order, right? Make sure John's not messing with you by changing the order up. Get the terms in the order that seems logical, and then say, what do I need to factor out in order to get this to be just a cute little x squared? And here we can see unequivocally, oh, it's this whole sum. I need to pull out the whole a plus b. Now, when I do that, the clouds will part and the glories will rain down, because now I'll just have a lovely little x squared. And then when I take it away here, I'll have minus x, which looks really nice. And then here it's attached to the end of the number instead of in front of it. Doesn't matter. I factor it out and I just get a minus 6. Oh. Life feels normal again, right? So factoring the sums isn't harder. It looks, at first your eye can go a little crazy because there's just so much going on. But once you get them in order and look at that first term, it'll be very clear. Oh, look, I just have to yank that whole sum out from each part. And then I'm left with this cute little thing. Let's factor it. We know it's going to be two binomials. We know they'll each start with an x. We know that it has to multiply to minus 6 and add 2. Remember, this is a minus 1. We can write that in if it helps us. I often call these angel ones because they're there if we need them. We might not be able to see them, but they're always there if we need them. So we can draw them in. So we're looking for two numbers that multiply to this and add to this. The little rule that I'm hoping to start to develop in your brain is that if this is negative, then we know that our numbers will have to be one positive and one negative, right? That's the only way to get a negative answer, is to have one of each. And we know that this number is going to represent the difference between these two. So I'm looking for a 1-point difference. So that tells me it's going to be either positive 2 and negative 3 or positive 3 and negative 2. I want it to end up as a negative 1, so I need the negative to be the bigger number. So this is what I want. Do you see? Instead of writing them out, I just made this like a little chart, right? With the positive and the negative at the top. And I choose this one because I want negative 3 plus positive 2. That gives me the negative 1. So positive 2 and negative 1, negative 3, I'm sorry. That is my answer. Am I right? Yay! And again, that quantity, that common factor, just sits out here on the front end of our quadratic expression after we factor it. It's not hurting anyone, it's just sitting there. One more. There are 3 of these. Here comes another one. Again, when you see them, they can look intimidating at first. But once you realize the pattern of what's happening, okay, so right away I'm suspicious, right? Right away I see this big sum and I go, ew, you're ugly, you are cute. Let's keep that in mind. Plus 9x times x plus y. Okay, cute and ugly. No offense, that's just how I think of it. And plus 20 times the quantity x plus y. Okay, so it becomes really obvious. This is what we pull out, x plus y quantity, and that leaves us with the cute parts, x squared plus 9x plus 20, x plus y. This time we know that our two factors, because this is positive, they're either going to be both positive or both negative, but we're going to add them together, right? Because they'll have matching signs. Positive 9, so right away I see, oh, it's 4 and 5, right? Because 4 and 5 add up to 9. X plus 4, x plus 5, yay. And again, once you get that quantity factored out, quantity is another word for a sum. An expression that needs to live inside parentheses is called a quantity. And that's how we say these parentheses. To read, for example, this line, I would say quantity a plus b times quantity x squared minus x minus 6. Okay? So that's the word we use to say parentheses. This is correct. One more. Are you ready? $72.3 factor. Oh boy, buckle in. This one's even crazier. All right, now I see right from the get-go, there's the part I like, there's the part I don't. Let's keep copying and see if it holds up. Okay, so I'm thinking this m times the quantity x minus 1. I'm thinking that's the part I want to factor out. Here it's a little bit confusing though because there's another x in there. Oh, but this, I want to keep the 7 and I want to keep the x, don't I? Because this middle term needs to be an x term. So that means these two go together to be the m quantity x minus 1 that I want to factor out. Okay, so it still works. And then here, this is the part I like, and this is the part I factor out. Okay, good, it's going to work. So I've factored that out, and I'm left with x squared plus 7x plus 10. Okay, so sometimes John will rearrange things in here, and you kind of have to sort through and look and see. It's okay to have this m. We just keep it over here on this side. It's one more piece being multiplied. If you wanted, you could put parentheses around it to show it's being multiplied against the others. It's fine to leave it without. Whichever you prefer, whichever looks more organized to you is fine. Okay, m times the quantity x minus 1. Now we need to factor this according to the usual rules. Positive 10, that means my two numbers are working together instead of being subtracted against each other. We're adding them because they're either both positives or both negatives. I see they're both positives, 5 and 2. Right? If they were negatives, then this would be a negative 7, but it's positive, so I want these. All right, x plus 5, x plus 2. And that's the right answer. Okay. Again, for now, spoilers, this just sits here. We don't have to do anything with it. We don't have to think about it. We just leave it be. Okay, that is the end of part 1. Now we are going to change gears. And we are going to talk about pyramids and cones. Okay, both of these objects are similar in that they start from a base and they rise up to a top. A pyramid, the base of a pyramid has straight sides. We're going to draw a picture in just a minute. And a cone, the base is a circle. Okay, so that helps us draw them. I'm not going to worry too much about the artistry of this. I just want you to see, for example, here is a rectangle. And then we can make a point up above it and then draw from the point down to each of the corners. It's not perfect artistry, but that is a pyramid. The base has straight sides and then it all comes up to a point. With a cone, even though we know it's a perfect circle, we draw it a little flattened so it looks normal. We put a point up and then we draw sides going down to the edges. And that makes a cone. This is like a traffic cone, right? The orange things that are out in construction sites. And then this is a base. Actually, they're cones on top of straight side bases, aren't they? I don't know. I think they are traffic cones, so never mind. Okay, so this is a pyramid and this is a cone. It's the difference between them. What they have in common is a two-dimensional base, right, that has length and width going up to a single point. That's what makes these two guys friends. All right, so what kind of calculations does John want us to do with these? He wants us to find the volume. So when we find the volume of a pyramid or a cone, well, let's see, how would we normally find the volume of something? We'd take the area of the base and multiply it by the height, right? But because with our pyramids and cones, right, we don't want all of the shape. If we just did it like the volume of an object with this base and went straight up, we would have a lot more volume included in that. I always think of it as a sculptor who has taken a block of something and he's carved away a lot of the top, hasn't he? He's left the bottom in the perfect original shape, but he's carved away a lot of the top. Same thing, this guy started with a cylinder of stone. Maybe it's a female sculptor. It doesn't have to be a guy, right? Let me just sort of sketch this in. They started with a cylinder. Pretend it's perfect, right? You can see. And then they carved away a lot of it. So in our formula, we have to carve away too. And the way that we do that is to take our usual calculation and multiply it by 1/3. What this means is that we're carving away 2/3 of that straight full object in order to make it come to a point in the middle, if that makes sense. So that's why we multiply by 1/3. We're getting rid of a lot of that material and we just want a little bit, we just want 1/3 left. Interesting thing is that both pyramids and cones work under this 1/3 rule. So that's kind of cool. Let's do a problem and I'll show you how this works. 72.4. Find the volume of the right rectangular pyramid. Okay, so here's the way the base looks. Okay, and we know that this is 9 inches and this is 7 inches. And then up here is the top of the pyramid, and then we see the lines going, oh, my proportions aren't exactly what I want them to be. Right? But there's our pyramid. And we knew that when we started, we can think of it this way. This was a block. Can you see it? This was a block of stone that came straight up from the base. It was neat and tidy. But now we've carved a lot of it away. And this top is now in the middle, on the top of our stone. So we have to take away all of this. So first we calculate what the volume would be if we hadn't carved it away. And we do the area of the base times the height. I'm going to write the whole formula here. Okay, so let's work on this part. The area of the base is 9 times 7. That's 63. The height, John shows us like this. He draws a dotted line coming down from the top and hitting the middle of the base, and then he draws a little right angle thing. Okay, that tells us that it's coming down from the center to the center. And he tells us this is 8 inches. He draws a little arrow like that. So we know the base is 63 because it's 9 times 7 times the height is 8. But because this is a pyramid, we want to multiply by that 1/3. All right? This and this reduce. This is 21. So the volume equals 168 inches cubed. Volume is a 3-dimensional measure. Okay? If this diagram confuses you, ignore it. Just pay attention to this cute little formula. It's super easy. Just remember the 1/3 means we're getting rid of some of the original volume because we've whittled it away. 72.5. How many are there? 6, 7. There's 7 in all. Okay. In this one, we have got a cone. It's a circle on the bottom, even though it looks a little ovally to us. It comes up, oh, pretend it's perfect. Okay. And we find out that the radius is 6 feet. And if you go straight down from the top to that center point of the circle and make a right angle there, that will be 8 feet. Okay, now we have to do the same thing. Volume equals 1/3 times the area of the base times the height. Okay, the base this time is a circle. Yeah. So what's the area of a circle? It's area of a circle equals pi r squared. So let's just shove all our numbers into one big calculation. The volume equals 1/3 times the area of the base is going to be pi times the radius squared, 36, times the height, which is 8. We can do all of this in one big calculation, right? But the area of the base is a circle, so I need the area of a circle. That's pi r squared. There's the pi. This is the r squared because the radius is 6. And then we multiply it by the height, which is 8. This is also in feet. I don't usually write the units, but I have been and I don't know why. This 1/3 is the fraction we use, like I said, to carve down from it being a full block to it being a pointy thing at the top. In this case, a cone. All right, let's reduce. Three into 36 goes 12 times. So then we're going to have that the volume equals 8 times 12 is 96 times pi. Cool. And that is a perfectly acceptable answer, or we can multiply it out and we could go 3.14 times 96 equals, I'm just doing multiplication here, 36. You do it too, and then we'll compare answers at the end. Oh, this is wrong. Okay. I'm giving you a minute to finish calculating. But there are two forms of the answer, 96 pi, or if we multiply that out, 301.44 feet cubed. Make sure you put an ending unit on these, all right? We can ignore it as we're working it, but at the end, we need to add that back in. All right, that was interesting. That was working on volume. Now we're gonna switch gears and look at surface area. Surface area, think magic wrapping paper, right? We want to cover the edges with no overlap. We want to have each area, each face, if you will, of the pyramid covered perfectly. Then we want to add all those amounts up. So let's work on that. These are always a bit of a process, aren't they? Okay, so what we have here, oh my gosh, that is not too good. Okay, here's the base of my pyramid. Here's the top of it. Okay, those sides kind of overlap, but you get the idea. It's 6 along the bottom. Find the surface area of this rectangular square pyramid. Dimensions are in centimeters. Okay, we'll remember that at the end. A square pyramid means that all of these sides are the same, and that means all of these triangles are the same. So let's cut it apart and see that what we're going to get is a base that is square, and we're going to get 4 of these triangles, right? I'm going to draw them out. They aren't all exactly the same, but they're supposed to be, okay? Because these are the 4 sides, right? Each one of these triangle sides is represented here. Now we know the base of each one is 6. We know this is 6 times 6. In order to find there's a piece of information that John's given us. Okay, what he's telling us is that the height of each triangle is 5. Base is 6 every time because the base of the triangle matches to the length of the side. So let's start calculating our surface areas. This is a rectangle, it's length times width, so it's 6 times 6 and it's 36, right? Now, this calculation is going to be the same thing 4 times. So I'm just going to show it once and then we'll multiply our result by 4. To get the area of a triangle, we do base times height divided by 2. In this case, this was 6 times 6. This will be equal to the base is 6, the height is 5, and we divide it by 2, right? So what we can do is we can simplify this. This is a 3, and we get that the area of each triangle is 15. And then we'll do it 4 times. You can multiply it by 4, but I'm just gonna add it up 4 times, and that gives us 60. So the base is 36 centimeters square. The triangles are each 15 for a total of 60. And then when we add these two together, we get 96 centimeters squared as the total surface area of the entire shape. Okay? So that's what we were finding here. That is reasonably okay-ish, right? Now we're gonna try finding the surface area of a cone, which is a bit crazier. This is example 72.7. Okay, this is our last one. Okay, so here's our picture. And we need some new information in this one, but I'll explain it as we go. Here's our cone, right? There's a measure that comes down from the center to the very middle of the circle. We call that the height. We don't know what that is yet. Then the radius goes out like this. We're told that 8 meters is the radius, and we're told that this measure, which is like the outside edge measured on the diagonal here, is 10 meters. This measure is called the slant height. We've never heard that before. This one's the radius. That's an old friend, right? But this is the slant height. It's not this. This is the regular height, but this is the slant height. Okay, to find the lateral surface area, lateral means side. We have a special little formula. Pi times the radius times the slant height. This L, this cursive L, is the variable we put on this. The radius, of course, we know is good old R, and our friend pi. Okay, so this is a new formula we need because we've never measured the dimensions of a cone like that before. We've measured triangles all the time, and that's what our last problem called for. But this one's a little different. So to find the surface area, we're going to have to find the area of the base, and then we're going to have to find the area of the sides. Okay? The area of the base is this little circle. We know that the area of a circle is pi r squared. We know that this radius is 8, so it's pi times 64, right? And let's do that on a piece of, no, let's do this on the next page. Okay, so I want to multiply 64 times pi. Ready? 3.14 times 64. Okay, let's do it together. You do it, I'll do it. I'll give you a couple minutes and then we'll compare. Okay, so 3.14 times 64 equals 200.96. So the area of the base is 200.96. It looks like meters is our unit, but we don't have to worry about that yet, okay? Now we need the area of the sides. It's all one big side, and we're going to use this, right? It equals pi times the radius times the slant height. So that will be 3.14 times the radius is 8 times the slant height is 10. All right, so we're multiplying 3.14 times 80. Let's go back over here to do that. 3.14 times 80. Well, we know this is just a 0, and then we'll go on. Okay. $251.20 is the product of those three numbers. And now we're ready to add this up. The area of the base is 200.96. The area of the sides, I say plural, but it's one big shape. If you've ever put one of those plastic collars on a dog, I guess they use them on cats too, but you know, so they don't like lick at their scar or stitches or whatever they have that they shouldn't lick. It's like that. It's all one big piece, but we bend it into a curved shape. And I hate those collars, and I never put them on my dog, even when they tell me I'm supposed to. I don't. Maybe that's why I dislike these problems, because they remind me of those collars. Okay, so we add together these two numbers, and we get all right, let me just double check that. 6, 1, 2, 5, 4. Beautiful. Meters is our unit. Surface area is a square. And that is our final answer. All right, so in order to do this, in order to find the surface area of a cone, we need this new calculation. This lateral surface area, remember lateral means sides. We need to use this formula where L equals the slant height, and we use the radius as well as pi. Okay. I'm almost done with this lesson. I just want to show you one more thing. On pages 292 and 293, you don't need your book. Let me just show you. There are a ton of terms that relate to pyramids. Here's more on pyramids, and then cones are down here. This is a ton of information. It's a bunch of vocabulary words. Things like altitude and vertex and lateral edge. I've taught you enough to be dangerous. I point you to this as a resource. If you're ever doing a problem with pyramids and cones and John throws a word at you that you don't know, come to these pages and see if you can figure out what he's talking about. I could explain all this to you now, but it wouldn't stick in your brain. It barely sticks in mine. It's a lot of tedious detail, and unless there's a reason to learn it, it won't stick in your brain. So, I've given you the words that are most important, right? This is the height. This is the radius. This is the slant height, this outside edge. You see what I mean? We've talked about some of that, but there's more detail in there that you may or may not ever in your life need. So, pages 292 and 293. More geometry terms. You might want to take one of those little post-it flags and stick it on that page so you don't have to scramble for it if you ever want it. But honestly, I don't know how much you're ever going to need it. Oops, did I say that out loud? Teachers are supposed to tell you, oh yeah, it's all important, but that's not the truth. So I'm just going to be honest with you. You probably will never need that, but if you ever do, I want you to know that that page exists. Okay, guess what? Lesson 72 is done. And I don't want to say thank goodness, but maybe I did. Okay, bye.